As I'm not available there, so I'm taking this session online. So, like, yeah, we'll start with the slicing process. So, in this session, mostly we will be looking into how additive manufacturing process flows and what are the different file formats we can use for 3D printing and basics of slicing, which I'll show it through the slicing software. Okay. So the integrity, like architectural integrity of this three-dimensionally printed objects is like mostly fundamentally dictated by the digital framework through which its geometric and functional data is communicated. So in the early stages of rapid prototyping, the primary requirement was the accurate representation of a model's surface geometry to facilitate the calculations of machine tool path. But now, however, as the industry has matured, the new era of additive manufacturing has come, and the scope of data exchange has expanded to include material gradients, complex internal lattice structures, all these things. You might have listened to Professor Somsekhar sir, tell. So now we will explore how, what are those different, we'll just glance a bit different files, and we'll just dig into how we can, slice that using some softwares which are available in the market. Okay. So, what is the additive manufacturing process flow is it's basically simple where you prepare some CAD model using some any CAD software, SolidWorks or Solid Edge, AutoCAD, anything, any software, but you have to save those CAD models in .stl format or any other format which you require. Normally, the easiest way to use is .stl format which we use, but there are some other dot formats which you can use it to input it as a slicing in the slicing software to input them as. So first we'll prepare CAD model, and then we'll convert it into .stl format, and we import that CAD model into slicing software. From there, we will do slicing in the slicing software, and then we can go for 3D printing, and that 3D printing object can be taken out. So this is the basic process flow, how our additive manufacturing works. So coming to STL, you might have heard STL already. Professor Somsekhar might have told you about this standard test selection language. It has two formats. One is ASCII format, another one is the binary format. So the STL format is implemented in two distinct encoding schemes, as I told. So these two provides a human readable text descriptions of the facet data. So which is like useful for debugging, but computationally inefficient. They can be debugged, but we cannot read a few things like out of two formats. One is readable, another one is not. Okay, a simple cube in ASCII format might require dozens of lines of text, while the same geometry in binary format is represented as a compact stream of machine codes. Okay, so if you so in as an outline, as you can see, in ASCII format, size is like uh, uh, it is very easily readable. Okay, but the size will be very big. It's like a endless loop of codes. But in the binary format, it's not readable, but the format, like, it's very size goes small. So these are the two formats which STL gets saved in. Okay. And coming to the different file formats which we have in 3D printing are STL, OBG, AMF, PLY. So all these formats I will like introduce one by one. In STL formats, it's so the STL format is established in like around 1987 by 3D Systems. It's one of the biggest manufacturing companies and design software makers. So they invented this, and an STL format describes the surface geometry of the 3D object without any representation of its color, texture or material properties or physical units. Okay, so the geometry is encoded as a list of triangle facets, where each facet is uniquely identified by two components, a unit normal vector and three vertices ordered according to the right hand thumb rule, where the unit normal vector. Okay, so the unit normal vector, a perpendicular line to the triangle with a length of one unit, specifies the orientation of the surface, so disguising the outside of the part from the inside. Okay, there is a mathematical representation as well for this, where you can do calculations and all those things, but that is covered in other lectures as well. So, the structural integrity of an STL mesh depends on the vert- vertex rule. So, which dictates that every triangle must share exactly two vertices with its neighboring triangles. So, this ensures that the mesh remains a closed manifold. Okay, a closed manifold polyhedron. So a condition often describes in the industry as being watertight, like where watertight in the sense it's completely tight inside. Okay. So if the vertex of one triangle lies on the edge of another, if triangle overlaps or leave gaps, the model is considered non-manifold and may result in slicing failure or structural defects in the physical prints. This is about STL, and most the drawback here is no information about color or material can be saved, or how the structure texture is, and it do not support assembly. So it should be complete whole part with as a single part, not as a assembly part, and accuracy is little bit less. Coming to the OBG, so this format emerged in after STL format in 1990s as a solution for the computer graphics and animation industries. Unlike geometry-centric STL, OBG was designed to handle a rich set of visual attributes. Okay, so it including color mapping or color texture mapping or material properties. So as adding additive manufacturing moved towards full color printing technology, so such as binder jetting or any materials jetting, so OBG became a preferred format for display models and artistic projects where appearance is as a critical as shape. So geometric flexibility of this object support, it's a significant distinction. There is a significant distinction between OBG and STL. It lies in types of polygon supported. While STL is strictly limited to triangles, OBG files can store quadrilaterals, hexagons, and other complex polygons, as well as freeform curve and the surfaces like freeform curves as well. So this geometric flexibility allows for a more efficient representation of certain shapes, often providing higher accuracy with fewer elements. So the primary value proposition of OBG format is its sophisticated approach to surface appearance. So this is achieved through multi-file package consisting of a .obg file and material, or maybe a MTL, like a material a template library file. And yeah, so the multi-file structure introduces significant logistic challenges. If the MTL file or the texture images are missing, then incorrectly referred, so the visual data is lost, leaving only a raw geometry. So where here, when I say MTL, so it is included in the OBG file itself, where it will give material properties and also the texture images, in which texture we need that printing to happen. Additionally, the inclusion of high resolution texture maps significantly increases the file size and computational load requires for the slicing. So coming to AMF file. So AMF file was introduced by the earliest of 2010s, and the limitations of STL as well as OBG became a bottleneck for advanced industrial additive manufacturing. So AMF is additive manufacturing file. And so the American Society of Testing and Materials, ASTM, they developed this AMF file. Initially, they used to call it as STL 2.0, but later they converted it as a AMF file. Okay, so AMF files utilizes an XML structure, which is extensible markup language, which ensures that the file is both human readable, easily processed by modern software. So the format is organized into five primary top level elements, such as one object, material, texture, constellations, and metadata. So metadata is like it stores like who is using, the author, and so licenses and units. So when it comes to constellations, it is hierarchically arranges the object in a build, like how it's like constellation is like how the building should happen. And then texture encodes image data for surface mapping, and material data again specifies material properties to each print, like which material we are using to print. And the object is defines the geometry and material association, how our geometry is there. Okay, so this hierarchical approach allows AMF to describe much more than just the skin of an object. It can define internal structures, material gradients, and even orientation of parts within a large manufacturing batch. The most significant geometric advancement in AMF is the support for optional curved triangles. Rather than approximating a curve with hundreds of flat facets, so AMF can define a curve mathematically using tangent direction vectors or surface normal at the vertices of a triangle. During the during your slicing or manufacturing process, the printer software subdivides these curves and triangles into subtriangles. So this is one of the file which we can save our model into. And the limitation of this is like software like which supports this file are very less, and hardware support for this is very less compared to STL and OBG. So the next file format which we have is PLY. So which is the polygon file format, so which is also known as Stanford triangle format, which was developed in 1994 to store data captured from 3D scanners. So we have certain 3D scanners where we just scan any 3D objects with its 360-degree orientation, and you'll get the complete file from that 3D scanner itself. So this was used to store the data which was captured from those 3D scanners. While less common, like this is very less common in general prototyping, uh, but it is like a standard for research and scanning heavy workflow. So where you are using scannings, then there this file format is used more. So PLY's strength lies in its flexibility, because 3D scanning often introduces sensor noise, and PLY supports the storage of data confidence values directly within the vertex properties. So this allows the researchers to distinguish between high precision data and interpolated points. So this is like a comparative analysis of all the file formats which we have. So if you take a overview that how do we choose, like how do we choose a file to our application, so that depends on what you need. So if you want you know easy to create and easy to understand, or if then you choose STL format, but there you cannot save your color or material which you are using, or the texture how it is coming to that is you cannot expect from STL format. But if you can use OBG file, then you have to, there you will get your color mapping and texture all. But again, here also you have some limitations where the file size will be larger compared to STL, and textures additional data which you might need or you might not need. So depending upon your application, you have to choose your uh, file format. So like coming to the slicing process. So first what you'll do, first you'll do a CAD modeling whatever is there. So for the ease of this flow, so we'll use STL file format. Okay, so you first prepare your CAD modeling, and then you put it in slicing software, and it will slice, like there you do like slicing, and that STL format which we input after slicing, that will be converted into G code, and you can visualize the same thing in the software as well. How it is going to print, how the layers are going being printed. So all that you visualize. If you need any changes, you do the editing, and then import that final G code into the printer controller. So this is how the slicing process goes on. Like first the CAD modeling, slice, and then after slicing, that will be converted into G code. That G code goes to printer controller. So yeah, in the slicing itself, you have a front end and back end, where in back end STL will be read, and slicing algorithm will be there, and G code will preparation will be there in the back end. So in graphic user interface, you'll see how the file is imported, how the file is being triangulated, and how that complete visualization and G code visualization also you can see in the slicing process itself. So in slicing, as we go on for the demo, you will get to know this infill. There are different process parameters which we have to define, like how thick our layer height should be. So if you're having certain material, you go with certain height of the material, or if you want to do some R&D with higher flow rate, then you go with certain layer height. So this can also be controlled. And also outer perimeters. So how many outer perimeters you need while printing, and how much should be the infill. So if you say you have a 10 cube, so in that you need like just 5 itself, or 2 per se, you need just outer perimeter, then you can give that. So depending on that, your properties of the print also will change. Okay, so infill patterns, there are different infill patterns, such as square, grid, or rectilinear, honeycomb structure, or cubic subdivisions, or concentric lights, concentric flow patterns. So yeah, where outer perimeter is as it will be same as the infill pattern as well. It will be concentric to each other. So these are the different okay, infill patterns. And you can also vary density. So how dense your material should be while printing. It should be 100% completely like solid you need, or just 50% density. So depending upon this as well, your depending upon the density, your strength of the print matters. Okay, so yeah, uh, so if you see here, you can see how your print quality depends on the slicing thickness. So if you slice it in a higher thickness, then you can observe how the print quality is. And if you check, just a minute, I'm just okay. So if you slice it in a lower thickness value, then how the quality of the print varies. So this you can just visualize with. So you should always go with the lower thickness to get a very beautiful outer structure, as good as possible, as good as your 3D model. But if you go with the higher thickness, then you should not expect good quality prints. And also that depends on the material as well. As you go on doing research into this field, then you'll understand how this varies, why it is important of importance of slicing thickness. Yeah, so this is one example where slicing thickness is varied and printed. As you can see there, completely this permits you to adjust the layer size as the print proceeds. So you can see while printing, if you have uh, connected it to the system, you cannot, like, also one more thing is you cannot change the thickness while printing. Okay, so you have to do it pre-slicing. Some systems are there which can be connected directly to the system, and you can vary it if it is connected to system and the printer where you are slicing and the printer, like where if you are doing real-time monitoring of the system and real-time controlling, you cannot expect this with the all the systems. So this is one example where variable or adaptive slicing strategy is done. This also you can pre-do it. It's like before slicing itself, you want certain section of your material to be printed with certain layer thickness, and certain section of this material, as you can see here in green and red zones. Here green is with 25 micron size, and red is 100 micron size. You can vary it before going to print, before converting the code into G code, like your model into G code. Once that is converted to G code, you cannot change anything. Okay, so let's take some. So this is the theory behind the slicing strategies. So let's take some one slicing model, and we'll do it in a slicing software. Okay. So yeah, here I have taken a Anycubic slicer. There are so many slicers which you can use for open source as well. There is Ultimaker or Prusa. Like this, there are different 3D slices which you can use, which are also open source. So here I will just show you one, and the slicing process is same in all. Just the thing is the user interface will be different, but it's almost the same. Okay. So first, when you open any slicing software, you will see the user interface something like this. So here you have to set, in this you have to set which machine you are going to use. So there might be different variants of the machine, and you can use different nozzle sizes there will be. So in this system, so we have a Anycubic Cobra 2, that is the printer name. So some of the printers are already inbuilt, or you can even customize it as well. It's not like you should restrict to the same, and some 3D printers are not there in this like they're not there in the like inbuilt list. Okay, so you can customize your own 3D printer, and you can save it. So here you have to give printable area, how much, what is the like printable area of the 3D printer, and bed area. Then again, what is the maximum height, that is printable height, and nozzle volume. All these things you can just check, and what is the uh, if it has cooling fan or not, or extruder clearance. So all this information you can put it in there. But or else, if you have some of the known 3D printers, then you just select it, save it, and close. Okay, so then coming to filaments, there are different kinds of filaments. So what kind of material you are using, depending on that, you have to set the printing parameters. There Here we'll be using Anycubic PLA material, but you have different materials which request different temperatures or different. It may be some 3D printers will allow you to change the diameter as well, and flow ratio. So a diameter here means the filament diameter. So whatever we are using here is 1.75, but it is not restricted to that. There are different printers which has different which can take different diameter inputs as well, and what is the density you want to give, and how much shrinkage it has depending upon the material, and the temperature also. So what is the recommended nozzle temperature? Here nozzle temperature means what is the temperature which is needed to melt that filament. So minimum to one maximum range you should give, and in that you should select it will you have to select what is the printing temperature as well, and printing temperature. So you have to select what is the printing temperature, and bed temperature. So When printing, while printing, you have to select the bed temperature, because while printing, the print will not stick to it if the bed is not uh, the accurate temperature which is required. Okay, so all these things you can select in this. And then cooling also can be done. How much, like, while printing itself, you should cool the filament as well, whatever is there, that you should cool. Like, you should maintain exact same temperature. It should not exceed the temperature which is required for you, or it should not be less than that. So that cooling can be done. And some setting overrides which we want to do, some advanced settings, all these things you can just look into it, and you can play with it, so that you'll know what are the changes we can do and how we can do. So all these changes if you do, and you can save it and close. As I have already saved, I'm not saving it another one. So here you have selected what filament you are going to use. So here you have to select what is the standard, like first filament layer height you need, first layer height you need, that you select here, any in which like printer you are going to do it. And coming to quality, so these are the some things which you have to look for. So what is the layer height you need in your printing? So first we'll go with zero 0.2 mm height, that is like a standard mostly we use. And there are some other things which you have to look for, like seam, how much you are giving, what is the seam gap. So these are all the formats which you can look into and do the slicing. And if you want, if there is any changes like line width and first layer, how much first layer, how much should be the line width, and outer layer, how much should be the line width. All these things, inner wall, top surface, pass infill, internal solid infill, what should be the size of that. So coming to the strength, the here the main thing is about sparse infill density. So how much dense you want your print should be. So I will show you some examples with the variation of infill density and infill pattern. As I showed you, there are so many different infill patterns, that is rectilinear, grid, line, cubic, triangles, all this. And you can vary depending upon your requirement. Okay, so each infill property gives you different properties of the print. Okay, so you can vary whatever you want in whichever format you want, and then how much you want it to be. So this is the one thing which you have to look for. And speed, so what is the print speed, like how much in what speed the printing should happen. You can vary it from 500 to 200 per second. So for a good quality prints, as the slow you go, that print will be good, but it should not be very less as well, that you should make sure of. Okay, so first, so here again in speed also, first layer should go up to 50 per second, and first layer infill. So, and then outer wall, how much it should be. So all these things you have to define, how much you need infill, and then what is the speed you need required for each part, and you can vary it. And then support structures. So support structure is like some certain, when I show the example, I will tell you how support structure comes. So at there is a threshold for each print. So if imagine if you have a, okay, let me take some model to show the support structures. So here you can see, go to files, and you can import whatever the file which is required for you. Okay. So you have taken one geometry here. So here you have to define in which direction you want this to be printed. So if you want this face to be printed on top, or if you want the other face to be printed, so that for that you can do changes here. So for movement, like where you exactly, so consider this, whatever the any cubic bed is there, it is of the same size of the bed which we have in the printer. So wherever you place, it will be printing at that position exactly. So if you move around using the arrows, or if you can just change the position here as well in the above section, if you just change the position as well, it will move to that position, and you can consider it there. Or if you want to change the different, if you want other face to be down, so you can just rotate it by using this option, where a coordinate will change. So yeah, so or you rotate it there, or you rotate it here, changes will happen, as you can see, right? Yeah. So okay, I wanted to show you the support, right? Okay, so I will take this into 45 degrees. Okay, just in case, you should not print it in this way. The tensile sample should not be printed in this way, but I'm just telling to show you how supports can be generated. Where, so if you want to print it here, it needs certain support, right? So in starting it can be done properly where it will start, but as you goes the angle increases, right? As you goes on in if as you move on the z direction, the angle increases. So while that angle increases, you cannot print in exactly the way you want. So there you need some support. It cannot print in the air, so it needs some support. To to do that, you have to enable the support in this section. And you there are different supports, like normal supports and tree. I'll show you both. So if there are some auto options as well, or if you want to change it to according to your requirement, then you can change it as well. Here also you can give a pattern and all those things. So after if I just slice it, as you can see here, the green part, whatever the green part is there, that is a support structure which was required for this. So if I change the angle again, so if I change the angle of this from, okay, say 45 to, I'll say I'll make it 60 degrees, we'll see what happens, right? Okay, let's make it 30. Okay, 60 is fine. See, only at the base part it is taking the support structure. Why is that so? That is because there is a threshold angle. Up to certain angle, it can print without support structure also. In this case, it is 40. So if you change it to less than, say, okay, if you change the angle and then slice. Okay, so now you can see the whole system, like whole print which is required. Like, so the orange part is the one which is required by us, like that is the part which we are slicing it. which was in STL format, and we imported it and we are slicing it now. We want that to be print. But if there are certain parts, this is just an example of a part where I have taken. There you will have certain geometries where the complete part will have some angle which is more than 40 degrees. So in those cases you'll need this. But in this tensile sample, in actual situation you don't need it. But just to show you how it works, or how why supports are needed, I'm just showing you this. Okay, so this is how the support works. Okay, so if you have taken the support, like this is normal support how it generates. So if you want to change it to different support where it will be easier for you to remove, so change it to tree support and slice it. So you'll see something like this where it will create something like a tree where it will support, and it will be easier for you to remove. So depending upon your geometry, you change what kind of support you need, what kind of what is the strength you need, and what kind of infill density you require. Okay, so let me give some examples for infill patterns. Okay, so as now you can see it is grid, right? So as you go and see, and it's like just 15%. Okay, for this we'll just make the design flat. Okay, yeah. So as we have given a grid there, so you can see infill pattern is our grid. So here the infill density is how much? We have given just a 15% infill density. So if you increase this to like say 50%, and slice it, you can see the infill density is increased. So this is how the density will change, and depending upon this your properties of whatever you are printing, the strength will change. Okay, so if you give completely 100% infill density, it will be completely densely formed, right? So you can see that it's like completely densely formed. So as I said, there was a perimeter. So here also you can see the perimeters, and here you can see inner wall, like what how much is the time required to print that inner wall, and how much grams. So total filament usage also can be seen here, and what is the like cost depends on how much you input there, how much was the your cost, and how much total time also will be displayed. So it will be not exactly 17 minutes 16 seconds. It will change depending on the prep time. So there will be a prep time where you have to heat the nozzle bed, so including that, but it is almost will be approximately equal to the total time of the print. And if you want to change this to honeycomb structure, and some 80% infill density, and if you slice it, you can see like that honeycomb is not exactly seen how you want. So we'll change it to 50%. see, you can see the honeycomb structure now, right? So like in this way you have different infill patterns where you can try for to get different properties from the material, different strength, especially from the printing whatever you are doing. Okay, so and here also color combination shows you that what is which one is the inner wall and what is the outer wall and what is the infill you're being done. So all these things can be covered. Okay, so this is how you do the normal outline, like outline for the 3D slides, printing slices. After this you just export the G file code to wherever you want and you save it in G code format, and you're good to go. You transfer this file to the 3D printer and you can start from there. The 3D printer demo will be given by other lab mates of ours, so there you can you'll get to know how it is actually transferred and how the printing process happens. Okay, so yeah, so I'm almost done with the presentation and slicing software. If you have any doubts, you can ask me or else the volunteers there who are there. So they are, everybody is very well versed with the slicing software, so they'll help you out your doubts. Even you can ask me if. Yeah. Okay, then I hope you guys got some insights into how the slicing is to be done. So if you don't have any doubts, or else you if you want to ask me later also, you can just email me. I'll just provide my email address. If you have any doubts, you can ask me later.
Hello.
Off the mic. Yeah.
Hello.
Yeah.
Yes. Thank you for the presentation. Does anybody have any doubt? If nothing, we'll close this demonstration session. Okay. Thank you, Vinayaka, for the session.
Yeah, thank you, Prachi, for hosting me. Thank you, all the volunteers, and this is your everyone. This is your first day at IIT Dharwad. Enjoy your stay, and I hope we'll see you again for some projects or anything if your ideas works out good for the future collaboration as well. So yeah, thank you.
Hello, Vinayaka.
Yeah.
So, Soma sir wishes to speak with you.
You should share what are you doing there.
Oh, yes, sir. So I'm a research scholar in, as I told, I'm a research scholar in M4DP lab. So there's a project, like sponsored project by Spark, Government of India. So I am in Virginia Commonwealth University, Richmond, USA. So doing some certain part of the project here along with my colleague Mr. Deepak Mudukavi. So here we are trying to manufacture some functional materials by using like uh, one of the 3D printing processes. So there is a project. So along with, as Professor Ravi Adimani sir has come, I am here at his institute only doing that collaborative project. Yeah. So
Deepak,
that's much. Yes.
where is Deepak?
Sir is there.
Hello, sir. Yeah. Am I audible?
Yes, yes, and proceed.
Yes. Yeah. Hello, all. This is Deepak. I'm a PhD student. So I just submitted my thesis, and as Vinayak was rightly mentioning, I was also involved in the same collaborative project, and we both are working towards this project on the functional materials at Virginia Commonwealth University. And all the best for your workshop, and hope you enjoy your stay there at IIT Dharwad. Thank you.
Questions from audience? Whether you completely understood the slicing software or still clueless about the software. So, okay. I think if there are no questions, I think they can leave the room.
Thank you,
Okay.
sir.
Thank you,
Thank you
guys,
for giving.
for joining us. Is it maybe it's early morning?
Yes, sir. 6 a.m.
Okay.
now. Yeah.
Have a good time.
Thank you, sir.
Thank you, sir.
And actually, if I think Rico is coming. If I, how about now? Okay, since we have half an hour, let me understand a little bit about what kind of problems you guys are familiar and what kind of problems you guys are actually looking. Maybe I'll just start interacting with more so that tonight I'll prepare some problems. Okay, so maybe you can start from this side. Do you have something in your mind that what kind of problems that you guys are working? Maybe you can start with Madam. Yeah. Okay. So maybe one of you note down their background. So now we will just go across all the participants, and then we will come up with some problems relevant. Okay. Yeah. So please go ahead.
So what we have is you know equipments used by multiple users.
Okay.
So because of wear and tear, there are certain minute parts which from the company we get it at a very high cost. So when we get it done through CNC machines and all, some will be durable, but some the durability will not be there. So
Okay.
we wanted to know more about it's like how to increase the durability and good materials used and
Okay.
the bonding.
Okay. So you are looking something uh, development part of it.
What we actually have like monitors, syringe pumps,
Mhm.
and infusion pumps.
Mhm.
So for those equipments wherein there are the wear and tear,
Mhm.
there are metal embedded with the
Polymer.
polymers
Okay.
and purely polymers also, ceramic ones. So if it can be mimicked
Mhm.
with a better quality and durability, that
Okay.
would be useful for us.
Okay. So okay, noted.
Any physical damages as
Right,
well.
right, noted. So, so if you would like to pick up one particular problem, so what do you prefer? Like, I know there are good number of interesting problems that are working with you, but are you looking something in a particular problem that you would like to solve, or something that you are interested in, something we kind of help you out in terms of development of such any product for that matter? Maybe let's start with the simple prototype, right? So and then eventually we can start building up in that direction. That's what I'm trying to understand.
If concerned with a new product as such, probably it would be a bone
Okay.
graft,
Okay.
in which there are cases wherein we have multiple fractures at the joints,
Mhm.
and CTM images would tell you a scattered image,
Mhm.
axial and
So are we
sagittal.
able to get the CT scan or MRI scans of any component?
No, bones especially.
Bones, will you
Yeah,
able to get
CT
now?
will be more preferable than MRI because
Okay.
bones are more prominent in CT
No,
scans.
you have the data now
Yes.
available?
We have.
Okay. So I think
So one case we have.
okay.
In that, what doctors wanted was a 3D reconstructed bone
Mhm.
in hand
Mhm.
before the surgery,
Mhm.
so that they can visualize it well in advance, where to put the screws,
Mhm.
where to actually
Get the physical
get
prototype.
get
Yeah,
it
I think-
aligned in the surgery
Okay.
time.
Yeah.
So
I think this is doable. I think at least we can see that prototype. So, but what we need, we can do a slicing, patching. I think Vinayak talked a little bit about. I'm not sure how much he was talking about like stitching, but I think you have the Mimic software. So Geomagic, something, I think 2-3 versions they have, where you can actually get the MRI scan data, and then you can actually convert it into STL file. And then once you have STL file, I think it is easy job.
yeah, the main agenda would be to join all those parts of
Yeah.
the bone
Mhm.
into a solid structure and get a
How
part
big?
of it. Bone structure with the dimensions as in the CT images.
So like the size that
Size
you're
of the bone.
okay.
If it is a fibula
Yeah, I
or
think
tibia.
get the data. We will see how
Yeah.
we can
I
actually.
don't know how to integrate that CT images into.
I think you can actually
We
use.
can get a 3D constructed image of
You
the
have the
bone.
3D constructed.
Yes.
Okay.
That I can have with the scattered bones at the joint.
Okay.
So you have to fuse those joints to to the bone and get a
We'll do one thing.
model.
We will connect you one of this participant, and then he will work it out. Whatever the.
That is one part of it. Like to start.
Yeah. Sure. Yeah. I think.
Take over with another person.
Yeah. You just tell your background. We will see what kind of. I know that we got the idea that while drafting some problems, we can see it. Yeah. Maybe. Yeah. Go ahead. Aeronautical engineering. Okay. So did you had any opportunity to come up with some problems or something like interesting that you feel that you would like to take? Okay.
Seminar. Will we have now we get first intensive kind of workshops.
Okay. So you are open for any problem. Okay. That's a good way to go. Yeah.
So like I'm in third year aeronautical. Currently, I'm pursuing third year aeronautical.
Third year. You are in second year. Okay.
So like what problem we are like getting nowadays, like in jets, especially in jets, the chamber like where the high speed air is combustion process where it takes place,
Mhm.
that part it gets more heated,
Mhm.
like in the process during combustion process. So the material or the part in the combustion chamber,
Mhm.
it's very vulnerable, like for high temperature it's like uh, it's very quite it will be having the time for repair, that thing is going on like for far like more.
Okay.
So the material or the part like in the combustion chamber, so what better materials we can use, material or manufacture.
Okay. So more of new material development. Okay. Good.
Good evening, sir. I'm Karthik, third year, second year aeronautical from KIT Coimbatore.
Coimbatore. Okay.
Problem is when an aircraft flies and in some emergency situation, aircraft has to land on the water. In some cases, aircraft land and the plane gets damaged. In some parts, it is safe. What if we try to build materials such as aircraft is safe, or when even it is when it crash land on the
On
land
surface and as well as water.
Yes.
Okay. Okay. Interesting. Just note down.
Good evening, sir. I am Sharmila from Alagappa University, a PhD scholar.
Okay.
I am working a first year PhD scholar. I am working in supercapacitors. So my HOD sir
So
actually
you got a counter person. Okay. Okay.
so my sir actually suggested that if
Any
we
chance you're junior to her? No, right? See, I guessed it a little bit, huh? Yeah.
yeah, so he suggested me if you could fabricate a device on supercapacitor using printing technology or something.
Okay.
So I have no idea of printing
Yeah,
technology.
she has all ideas now. Okay. You can go ahead. Yeah.
So
No, I got
I
it.
had to fabricate a device for him.
Sure,
So
sure.
for
No,
that.
Yeah.
Good evening, sir. I'm Swati. I'm a PhD scholar. I work with composite
Same
materials.
college?
No.
Okay.
I'm from Bangalore.
So next time don't sit each other if you're from same college. Yeah. Okay.
I'm from Bangalore.
Okay, from Bangalore. Okay.
Yeah.
Composite, you said.
Composite materials.
Yeah, we have actually, filament extruder. So where you can actually prepare your own composite structures. Like
Yes.
example, you want to add some carbon fibers, or you want to add metal fibers, or you want to add aluminum or brass, whatever.
Actually, for the work, what difficulty we found is actually we wanted to do with FDM process. But then preparing the filament with little quantity for our samples was difficult for us.
You can put directly pellets.
Yeah, but pallets combining, we need a mixing of two different materials.
Yeah.
So that was difficult for us. So we had to go with the SLA
So
process.
I think we have used, right, dimethyl chloride. We have used it.
Okay.
So you can actually use
So
that.
you wanted to do with microparticles of boron nitride
Okay.
with the polymer resin. So
Yeah.
we wanted to combine and get a with different percentage. We wanted to combine and get the filament done. So
again, I am saying it. You don't need to actually prepare a filament.
yes.
Right?
Directly, you're asking us to
Just
use
to
the
prepare the pellet,
palette and
and
then
then little cut it into smaller pieces,
yes.
and then actually we put it under. Directly we have that pellet extruder.
Okay.
So there itself you can put. You can actually avoid a intermediate step.
Yeah, but then also we used SLA process, that is stereolithography process.
Okay.
There the difficulty what we found was the uniform distribution of the material was not possible.
Yeah. So I don't think we experimented with SLA or because so that is standard resin we actually use it.
Yes.
I think we have not tested adding any fibers.
Yeah, when we add the ceramic compounds in it, so uniform distribution in the samples is not achievable. So that was a difficulty we found
Yeah,
in
because
SLA process.
your density of the
material varies.
the powder
Yeah,
is
yes,
actually
yes.
different.
Yes.
So as soon as you actually put the material, it will
Actually,
will
we used a
settle at the
magnetic
bottom.
stirrer to actually prepare the sample. So once we start printing, the material is getting settled down because of the variation in the densities.
Right. Yeah.
So
Yeah.
that difficulty we found in SLA process.
Yeah. So you just visit our extruder,
Yes.
and then you will get some idea.
Yes.
Okay.
Yes, sir. Thank you.
Yes.
So, second year BTech,
Yeah.
civil engineer.
So you have to start actual projects.
Yeah.
Okay. You're open.
Yeah, open.
Yeah.
Open to it.
Or name you want? Maybe you can start with madam. What is her name? Abhishek. Ramya. Karthik. Sharmila. Okay.
Gangadhar. Gangadhar.
Gangadhar Reddy. Yeah. Sai.
Sai Priya.
Sai Priya. Yeah, some of the names are a little bit familiar, so don't feel others bad. I don't remember many names usually. Yeah. So you are also in second year,
Second
right?
year mechanical
So
and
you're
aerospace.
also open, or you have some?
Open to problems, sir,
Yeah.
but currently we are working, both of us and the team, we are working on building a CubeSat,
Mhm.
one new CubeSat.
Right, right.
So for that, we are searching for better materials. Usually everyone is using aluminum alloys or
Okay.
stuff. So
Okay.
that is one problem, and also the material. Maybe we are exploring thermoplastic composites or
Mhm.
something. Which
Yeah, I
will
think that is similar, like what she was talking, Sharmila talking. So where you can actually, vary the compositions or modify the when you actually prepare the filament or the pellets. So and then try to print it and see how the printing will come. Maybe initially you may fail it, but I think you will be the first one to do that kind of activities. Don't think that if you're actually trying something and then you fail it, like when you try to extrude material may not come out, right? It will somewhere it will clog, right? It is okay. After 10 days it will come out, but that is the first step that you can actually start, right? You can start, no problem.
My name is Karthik and I am doing my final
Oh,
year
there are two
BSc
Kartiks.
Physics.
Already one Karthik is over.
I like to study the post channeling techniques, how they affect,
Okay. Yeah. So post processing. Yeah.
and if the orientation affect the properties. Like if we take a magnetic substance
Mhm.
in 3D printing, if the orientation affects the
Yeah.
magnetic.
Okay. That is, I think, we have quite a good number of samples.
So myself Shankar Ganesh. Also open to problems.
Okay. So you are in PG or
I'm a PG student.
PG student? Okay.
But currently I doing a project with my final year project in FDM printers.
Okay.
I'm here to know about uh, how to make filaments,
Okay.
customized filaments, and extruding technologies.
So our extruder is working. Okay. Two are there, right? Okay. Okay. That filabot is working or not? But that is other one is new one only, right? Okay. Okay.
The assigned topic is related to this topic.
FDM. Okay. Fine. That is doable. We have good processes actually established.
Okay.
Yes, sir. Dan and sir. Yes, yes, yes. Okay. You are in which department there?
Mechanical engineering.
Okay. Oh, okay. Okay. No problem. Okay. I think note this again composite. So there are good number of composites people here. Okay. Srikanth.
Preparing the data set of cracked biomaterials, 3D
Okay.
printed biomaterial. That one of the
yeah,
PLA.
that we can look at. Those two are our students. You can pass mic to. Oh, by the way, so these are maybe partially they have seen it and then joined as interns. You can introduce yourself, which college you are from, and then what you guys are doing as an intern. I think we have 5 interns, right? 1, 2, 3. What are other 3? 2. Back end. Okay.
Good evening, everybody. Myself, Janvi TM. I'm pursuing my final year masters in machine design itself. Here we are working as intern. We are from University BDT College, Davangere.
What are you working?
My project is focusing on the materials SS420 and reinforcement is added as silicon carbide, and we are still doing trial error.
Yeah.
Good evening, everybody. So, I am from UBDT College of Engineering, Davangere. I am an intern here, and my work involves polymer and silicon carbide as the main materials. So, the main aim is to enhance the wear of whatever material I'll be creating at the end. So, to enhance the wear property of the uh, is the main objective of my work.
Yeah. Thank you. I think one more is there.
Good evening, everyone. I am intern in IIT Dharwad. I am intern in additive manufacturing and 4D printing lab. To complex design to easy and wet decreasing in aerospace and mechanical engineering. I have completed mechanical engineering from IS Institute of Technology and Management Bhopal. Thank you.
Yeah. Thank you. So other two are back end. They're working. I hope you'll meet them soon sometime.
Yeah. I am Ramit Chugh. I am from Bhilai, Chhattisgarh. I have submitted my PhD thesis.
Okay.
So my domain was in the solid mechanics background, stress analysis in singularities, machine components having singularities. So that
Okay.
was my domain. So I worked in the experimental part of that, and to make that specimens, I used the 3D printer.
Oh, okay.
Yeah. So I have two problems. The
Yeah.
first one is that to make the mold,
Mhm.
in making the mold, I use the 3D printer to make the patterns, and I used liquid silicon rubber to make the final molds.
Okay.
So is it possible that the main problem with 3D printer was that printed mold was that it was solid, and when we pour epoxy in that, it is very difficult to take it out.
Mhm.
So we used liquid silicon rubber as it is very flexible after solidification also.
Right. Right.
So is it possible to directly print something with the 3D printer that remains flexible after the printing process?
Okay.
Yeah.
I think you can suggest some material that we have, no, that flexible material. You can suggest.
Because when we pour epoxy in the mold, it gets a little bit heated up also.
Okay.
So it should not react with the
Mhm.
resin. And the second is that as in the presentation they explained that lattice structure is having a lot of effect on the strength of the final product.
Right. Right.
And physical testing is required for different things to check what is the strength, tensile strength, compressive strength of different products.
Right.
So if we can train a machine learning model to predict what will be the final strength,
Mhm.
we can use physics based machine learnings to predict in the software, slicing software, or that software only, that can tell what will be the effect of this lattice structure on the final strength of the material.
Okay.
Yeah.
That's interesting. Yeah. Let's see how far we can go.
Yeah, thank you.
Yeah.
Good evening, everyone. My name is Saurabh Kumar Sahu. I am pursuing PhD currently, and my PhD topic is machinability analysis of Encula 825
Mhm.
during turning operation.
Okay.
So, I bifurcate my project into three parts.
Mhm.
First is machining parameter optimization during turning of Encula 825, and second is I'm working on the cutting tool.
Mhm.
So coating and treating tools I used,
Mhm.
and comparative analysis of that.
Mhm.
And then the third part is my cutting environment, that how cutting environment affect the performance of the machining of the Incula 825. So currently I'm searching for the new area where I can go for the, like, I I'm not going to IIT Madras, but I heard that they are working on the 3D printer of the metals,
Mhm.
like nickel alloy, hard to cut materials. They are using in that using for the 3D printing also. So I am looking for the opportunities where I can go for the micro machining. Like as I asked previously, that post processing of the metal 3D printers are there.
Mm-hmm.
So I'm looking for the problems faced during the post processing of the additive manufacturing.
Okay. Okay.
Yes.
I think that is, I think, doable. We'll see.
Yes, yes.
Good evening, sir. I am Ganesh Malagali. I am working in SDM hospital as a biomedical technician.
Okay.
Currently, I am doing a project, medical device tracking system with IoT based.
Mm-hmm.
It's almost done, sir. Now I am stuck because of making a module,
Mm-hmm.
because I don't know how to use the 3D printing software.
Mm-hmm. So our students will definitely will help you out. You know, they have series of demos are coming. I think I'm pretty sure you will get a better idea, and you can ask any question like in terms of say example you have particular question how to you know you know stitch like repair, you want to repair some parts like broken STL file, or you want to completely start nothing, you don't know anything about, but you just want to show, you want to see how to create a CAD or a three-dimensional file, and then how to convert or how to export. So from there they can actually help you out to the level where you can actually plan in terms of path planning and then strategies, etc. Just feel free and then stop them, right? So and then I'm pretty sure that they will be able to help you out in all the demo parts. How many still we have some software demos? Hmm. Okay. Yeah, so I think you can reach them. We will help you out. I think when you actually start working on a problem, and then you are, without even, you know, your knowledge, you will start using the softwares, right? Without you, I mean, it's a basically that those are the basic. Like example,
Yes.
if you want to actually print one part, the basic thing is you have to create a file, or you have to create a three-dimensional file, and then the next basic is you need to convert it to STL file, and then you need to actually slice it, and then what kind of path plan. So that will come automatically. So and then which means you will actually learn as we go along.
I have one more question, sir. Is there any chances of a shrinkage while printing, sir?
Any chances of
Shrinkage?
yeah, definitely. I think any metal 3D printer, if you don't maintain parameters, and if you don't maintain proper in terms of melting, and then further layers, it will happen, shrinkage will happen. Yeah.
Thank you, sir.
Good evening, sir. Myself, Mahavir Jain.
Okay.
I'm also from STM Medical College.
Oh, one,
from
two,
three.
three. Okay.
Madam.
Oh, four. Okay. Okay.
Question is also same, sir.
Okay.
We are looking for a module and recreating of the spare parts
Okay.
of the equipments.
Okay. Yeah, I think we will see again. We'll see how best we can do. But since you guys are from STM, I think I don't see much difficult. After even the workshop that coming and doing, I don't think you'll have any big issues. Yeah, I think let's start with the one problem, and then see how it will move out where we'll move.
Okay. Thank you.
So he agreed. Whatever you guys will go, I'm fine.
Good evening, sir. I'm Satya Jyoti. I'm a PhD research scholar in VIT Velu.
Oh, there are quite a good number of PhD scholars here. Okay.
Yeah, I have joined in the month of August.
Okay.
Currently, I'm
You
doing
completed
literature.
coursework or still going on?
Yeah, I completed 3 courseworks and 3 is remaining.
Okay.
And I plan to work in supercapacitors.
Supercapacitor.
Yeah,
See, what you are here?
No. Sir. So especially I plan to work on pseudocapacitors.
Okay.
What my main motive of is my material should be biodegradable and it should come under green electronics.
Okay.
So the pseudocapacitors is classified into polymers and metal oxides. So I thought of I can work on polymer. So it will come but polymer material it's not actually biodegradable. As Ravi sir also talking on morning, he told he had at carbon nanotubes. Specifically, they add carbon materials to increase the specific capacitance value. It's quite normal. But what I want to do is I want to add a polymer and then carbon materials, and I want to add another material so that what to say, my energy device should be biodegradable.
Okay.
So I want to know what composite materials I can use.
Okay. So
Totally.
you want to get the another biodegradable polymer, and then you add it to the existing. Okay, makes
But
sense.
I want the capacitance value also at
Yeah,
the same
without
time.
losing the functionality. Okay, makes
Yeah,
sense.
and why I came here is we can make electrodes by using 3D printing also. So I want to know the exposure of 3D printings and
So
softwares.
one person is trying for last 1 month. Let's see.
Yeah, and then and further I'm planning to work on micro supercapacitors, which is
Okay.
included in laser,
Okay.
such as laser centering, and I want to know exposure so that I came here to lasers also.
Okay.
Thank you, sir.
Good evening, sir. Myself, Jyotika, and I'm currently pursuing PhD in VIT Vellore.
Oh, VIT Veller. Oh, nice
Yeah.
place.
And I'm currently working on computational material science,
Oh,
mainly
material science.
focusing on
Okay.
solar cells.
Oh, okay.
I just wanted to explore more softwares. That's why I came here, sir.
Oh, good, good.
Yeah.
Thank you. It's long journey. Yeah.
Good evening, everyone. I am A. Anis Fatima, and I am from VIT Vellore, pursuing first year PhD. And I am also working in micro supercapacitor, and myself and Satya Jyoti are working under same guide. So she is working on polymer based electrodes, and I am working on transition metal oxide based electrode. So our aim is to mostly the people who are working in material science focus on developing conventional method based supercapacitor. Like nowadays wearable devices, flexible electronics has been which is used for implants also. So that is why we are aiming to develop micro supercapacitor. So we don't have that much exposure in 3D printing, and also we came here to learn 3D printing, and also if we get chance we can implement our research problem into it.
Okay.
Yes.
Sure.
Thank you.
I think one more person. Yeah.
Very good evening, sir. I'm Tejashri, pursuing my bachelor's in third year biomedical engineering.
Okay.
There are two aspects which I'm interested in. Firstly, it will be the functioning of the brain, or in the morning session, I was quite excited when they spoke about the brain photon. And second factor would be robotic arm for self-assistive devices, or even a prosthetic limb, wherein the material has to be biocompatible and at the same point light and has to last for a longer amount of time. These are the two places that I'm interested at present.
Okay. So that's, I think, interesting. Anyone else left? Okay. So I think the reason why, morning I was thinking I will actually float the problem, and then I thought I'll ask you to choose it, but now I think changed it slightly. So how about doing a slightly different uh, way? Uh, so can we just go form the team by yourself? Say 4 per group, and then start discussing, and then see how you can actually converge. Sometime you may have a group, maybe 4 different problems, right? Or maybe 10 problems, but you start writing it, and then see and then put them together, and then tomorrow you will have a lab tour. Then just go around and then see what kind of facilities that our volunteers actually will take you around, and then you start converging your problem. So that is one way of thinking. So other ways, now that we got the areas that we have actually from all the participants, so our volunteers and myself will sit together, and then we'll prepare some 10 different problems, and then we will actually will float, and then you can actually form a team by yourself. Which one you prefer, let us know. You want by yourself, or should I we pick the names and then group from the group? How you want? So I will put something like a. Usually I'll do this mixture: one undergraduate, one postgraduate, one PhD. So this is a typical thumb rule that I actually apply whenever I form a group, so that you have all the brains in the group, so that you can actually work effectively. So is this fine? So now I see that good number of bachelors, good number of PhDs, and then good number of PG students as well. When I say PG, they may be doing PhD. When I say PhD, they have completed a PhD, or they may be advanced level. So if they are advanced level, I consider them already graduated. Okay, so it's just a matter of time, right? So so can we go with this way? So what do you prefer? Like, you prefer coming up the problem by yourself, or should we come up the different problem, or how? What can you raise a hand? Let me see how the number for first option one. Option one is, I'll repeat. So you will actually will sit now, maybe say now it is 5:30. So I will give till 6:30, or you take a whole night, and tomorrow morning we will again come back, right? And many of you are actually staying in the hostel. How many of you are staying in hostel? Quite a good number, right? So I think fantastic. I think morning, I think evening at 6 o'clock, you just take a tour, campus tour. You will get many ideas. Such a nice weather you'll have inside the campus. You'll find a beautiful place, right? So you will get really good ideas also. So this is the first option. So that you'll have time till tomorrow morning to come up with some interesting problem, right? So second option is, we will take a whatever the areas that you have mentioned, and then we'll prepare some 10 different problems, and then we will give one problems to each group. So approximately, if I'm not wrong, we have about 40 plus, which means 10 different problems will be floated, which means one problem for four members. So that way we can actually move forward. How many are okay for option one? I thought many will go for this option. How many are okay for option two? So how many are other? What are the other options you have? Huh? Oh, anything is fine. Sorry, this part I. So there was this. Still, it is record. I think you can remove the record.